So today I would like to show you some Kmaps examples and at the same time do some problems with standard sums of products forms and products of sums forms straight out of the Kmaps. So for the first example, we're going to use the function shown here, designated with the ones. Everything that is not marked, every box that is not marked, is assumed to be a 0. So think about how you would do this. You can pause the recording and think how you would do this and then compare with my solution. But my solution would be the following. If you look at these two ones and then these two ones, they are adjacent. They can be grouped together because if you remember, the map uh, wraps around, so these two can be grouped with these two. All right. So if we do that, we're going to get a term that is going to contain two variables less than the original. So if the original were 4, A, B, C, and D, when you group 2, you eliminate one variable. When you group 4, you eliminate two variables. And what variable is that going to be exactly? Now, you see, this group here is the intersection of this strip right here, the horizontal top two rows strips, and the two vertical strips that are at the sides, which correspond to D naught. Okay, so this one and this one, they correspond to D naught. So the intersection of D naught and this strip, which is basically the strip for A naught, okay, would be it. So these terms are described by the term A naught, D naught. All right, next, and let me change color. I'm going to use a different one so that you can see what I'm doing here. So next, we can take this group right here, this group of 4, and this group is simply this column, which is C, D naught. Then we have this one left. This one is not covered by any of the other two terms. So we're going to take this one, but obviously we have to try to take the maximal term, which consists of powers of 2 of adjacent ones, to get it covered. So instead of taking it just by itself, what we're going to do is we're going to, let me change color and use a green this time. So we're going to take these two together, okay? Because this term is bigger than just this one and contains it. The fact that this one is counted twice does not matter, as are these as well, okay? As a matter of fact, if it wasn't for this one down here, okay, we wouldn't even need this whole term. But we need it because of this one. And all of this term is going to eliminate two variables. So then this is going to be part of a group that is expressed with two variables as opposed to just this one, which is expressed with just 4 variables, with all 4 variables. All right, so now what do I have? Now the expression that I have is going to be, like I said in the very beginning, the red group is going to be A naught and D naught. And then the purple term is going to be C D naught, and the last term is going to be, the green one, is going to be the intersection of the strip AB, okay, and these two strips, the vertical ones, that correspond to C, okay? So I'm going to have A, B, C. So that is the expression that comes out from the Carnot map for all this function. Now notice that this function originally contained 4 plus 2 was 6 and 1 is 7, 7 minterms, okay, of 4 variables each, in other words. But all of that was reduced to just this, which is also, notably, a sums of products form. So what we have learned so far is to actually get a sums of products form straight out of the Carnot map. Now, what would happen if I wanted the products of sums form? Now, then you could take this whole expression and do what we learned to do with manipulations. So take the complement of it twice. The first complement is going to turn this into a product of sums form, but that would be the product of sums form for the complement function, and then you would have to carry out all the operations to turn it again into a sums of products form, and then use the second complement to convert it back into a product of sums form, but this time it would be for the original function. All right, so that was the summary of what we learned to do previously. But now, notice that I can take all the places where I have the function being 0, and that would be the complement function. So in other words, I can take a shortcut and take the sums of products form for the complement function, okay, for the complement function. And then once I have the sums of products form for the complement function, then I complement that one to get my original function, and that would convert the sums of products form into a products of sums form. All right, let's see how this is done. First, just to make sure that we're not going to have confusions, let me just put the zeros where they belong. So this 0 belongs here, and I need to put some more, oopsie, I need to take these two and move them over here, and then I need these ones here, and I need these ones right here, and I need one more, which should be right there. All right, so here's my function now. I am after a product of sums form, and so I am taking the complement function. So then I'm looking at the zeros. So I want a reduced form expression for the complement function. Again, think how you would group these zeros in order to make the maximum eliminations. Now, there is actually a lot of interesting terms here. There is one term which is this one. There's this one, okay? And then there is, see, where's my cursor? And then there is this one right here. All right. Now there is also another interesting one, which is this one, this column right here. Now that is not going to be useful though, because it covers zeros that are already covered by these two other terms. Okay, and these other terms I have to take. I have no option. For example, I have to take this one. Okay, and the reason that I have to take this one, um, the blue one right here, is because of these two zeros at the spots 8 and 12. All right, those cannot be grouped with anything else. So I have to take this big group right here of 8, 9, 12, and 13. And because of the zeros at the spots 3 and 7, I have to take the green term up here. All right. So these two terms that I must take, they already cover the zeros that are in the column C0 and D. And so I don't need to have this term taken. Now, I have taken all the zeros except from one, which is this one in the spot number 11. So what do I do with it? You might think, okay, for this one, what I need to do is I need to go like this. Okay, you would be tempted to say that, but that's not right. That's not good. The reason it's not good is because this term seems okay, but there is actually a bigger one that contains these two. And that is if you consider the fact that the map wraps around, you can take these two terms, with these two right here. All right. So now these red terms will do. Now, if I call my function f, then what I have here is the complement of f. Okay, so f complement would be all the terms with the zeros. So the green one, this one up here, what is that? That's the intersection of these two strips, the two center strips of the columns, okay, which correspond to D, okay, D. And the first two rows, which correspond to A prime, A naught, okay. So this one here would be A naught and D. That's the green term. And I need the blue term, which is going to be the intersection of these two rows and these two vertical strips right here. Now that is the intersection of A. A is these two strips together, okay? And these two columns, which correspond to C naught, you see? C naught. Okay, so I have A, C naught. And then I have the red group, which is these four, these and these, which is the intersection of the center two columns, which correspond to D, and the first and last row, the strip of the first and last row. Remember that the map wraps around, okay, vertically as well as horizontally. So this strip and this strip right here correspond to B naught. Okay, so it's B naught that does not change in these two strips. So then my result becomes or B naught, B naught, and D. I'm sorry, I need to be able to write here. So, or B naught and D. There you go. So this now is the expression for the complement function. So remember that this one up here, it was F. F is all of this. Now this one over here is the complement of F. Okay, this is the complement of F, and it is in sums of products form. Since I'm looking for the product of sums form of the original function, I can take this one and complement it. Okay, and that would be my function F again. So F would be the complement of all of this. So if I take all of this, copy it and go and paste it right there, and then I go and complement all of this like this. Well, can draw very well with a mouse, but I was trying to just put a complement on the top of that. Okay, so um, let me try to redo this so it's not that ugly. So I have this, and I need to make it a little thicker. So all I need to do is just do this. Okay, that's a little better. All right, now then this becomes equal to, I applied the Morgan's law, and then I have what? A naught D, and then the complement of that. I'm going to have to draw it later. And then and AC naught, and then the complement of that, and then B naught D, and now I'm going to have to make the complements for all of those. So complement of this, and complement of this, and complement of this. Okay, now remember that the original complement has broken down into individual complements and has turned the OR operation into an AND. Now I go back to my expression and I continue. So if you continue from here, I take the complements. So the very first one becomes, I invert the variable and the ends become ORs. Oopsie. A and D naught. And then I have A naught or C, and then I have B or D. All right, and that is basically it. As you see, these complements here changed the ends into ORs and inverted the variables. And so what I have here now is in fact a product of sums form that is for the original function. Okay, because I started with the sums of products form for the complement, but I complemented that, so I got my original function back, and then the sums of products form turned into a product of sums form because I only used one complement. All right, so I hope that you get the idea here. You want a sums of products form from the Carnot map, take the ones and try to get the minimal groups as usual. You want a product of sums form, then you take the complement function, so you go after the zeros, and you do the same thing as if the zeros were the ones. Well, the zeros obviously would be the ones for the complement function. And then you do the same thing, getting the uh, sums of products form, the reduced sums of products form, uh, and then you invert it to get the product of sums form for the original function. Okay, now this implementation right here, the product of sums, excuse me, the sums of products form for this function will give you an implementation in terms of and, or, and not gates. Now remember, if you want to use only nands or nors, then you use the trick where you complement twice. So if you want a one of those implementations, then you invert this twice, and what's going to happen is you're going to get a NAND only implementation. So let's see how this thing works. Let's take this one and copy it and put it down here. And then what we're going to do is actually need to move it a little bit. We're going to complement it twice. So I'm going to take the complement and the complement. So one complement, and then I need another complement. So I'm going to use another color because I don't want to confuse them. All right. So now I have my expression again, which I'm going to paste right here. And by using the first complement, I'm going to have the following. First, I need to leave the red complement as is. So the red complement is staying as is. The green complement will turn the pluses into, the ors into ends. So in the expression, this is going to be ends. So this is going to be an end like that and like that. And of course, what I'm going to also have is the green complement. I need to select the green color. I can't see where my cursor is. All right, there it is. So I have a complement for this term, and then I have a complement for this term. Okay, that's really pathetic, isn't it? So right there, and then right there. Okay, so this shows that I have NAND gate here, and a NAND gate here, and a NAND gate here. And then all of these three terms, they're combined with another NAND gate, which is the red one. Okay, and this is a NAND only implementation. This is nothing new. It's the same thing that you heard before. Um, you get a standard sums of products form, and then you complement twice, and you end up with a NAND only implementation. Now, what happens if I want a NOR only implementation? Then I take the product of sums form. So now what I'm going to do is I'm going to go for this one. Okay, so this one here, if I go and paste it right there, then I can complement it twice as usual. So I'm going to have one complement right here and another complement. Um, let's see, another color. Well, they're not that different anyhow. All right, so then what I'm going to have is that this becomes, let's see, what does it become? I'm going to have a complement over here, and then I'm going to have some smaller complements here and here and here. But before I go there, I need to also change the ends into ors. So this is going to be an or, and then this is going to be an or. And now I can complete the rest of the complements. So I have a complement on this term, and then I have another complement on this term, like that. Okay, so this complement changed the ends into ors and complemented each term. Now, don't get confused about the fact that each one of these terms is a composite term. It's okay. The, the complement is there. It complements the whole term. Now, I can take this inside here, but that, what it would do is it would turn the or into an and invert the variables. So if I did that, if I proceeded, I would get an expression over here that would not really be nor only. This one, if I stop at this point and don't do anything more with these little complements, okay, then I have a nor only implementation, because this is going to be a nor gate right here, and then I have another nor gate, then I have another nor gate, and then all of the three terms will be combined with a NOR gate. So I have a NOR only implementation. Okay, so here's another example, and again, try to think how you would do it if you were to do it by yourselves. And we will do the exact same thing. So we're going to get the SOP form, the POS form, and NAND and NOR implementations. All right, so to begin with, there are some telltale stories here that will help you figure out what you need to do. If you take a look at this one right here, what can it be paired with? The only thing it can be paired with is this, all right? So you're going to have to take the following term. This term right here is one that you have to take. This one is an implicant. It is also a prime implicant, because there is no bigger term that contains this one. So that's a maximal term, so that's a prime implicant. If you take a look at this one, the only way that you can have that one covered is if you take it in conjunction with this right there. Okay, and then we have these ones over here. So this one will force us to actually take two groups. Now, one might be tempted to do the following. Let me change color and use green. So one might be tempted to do this, take these three terms together, but you cannot. You cannot take those three terms because they're not a power of 2. You can only take 2 terms or 4 terms or 8 terms, but have to be a power of 2. So you will find out that there is no way that you can express this area right here with a reduced number of variables. Yeah, on one hand you have the strip, which is the strip AB, okay, which intersects with what? It intersects with these 3 columns. But you cannot express these 3 columns in an easy way. 2, you can. So these 2, for example, will be D. These 2 will be C. Okay, but you can't, there's no way that you can take all 3 of them together. So you have to break that up. Okay, and if you break it up, you're going to have to take these 2 terms. Okay, and this one is in fact an essential prime implicant. It's prime because it is not contained in any other term, and it is essential because you have to take this term because of this one. The one in the box number 13 doesn't pair with anything else. So this term is the only one that the only maximal term that will cover it. All right, so you do that, and then you need to take the last one in box 14, and in order to do that, let me change color again once I find my cursor. All right, I'm going to use this purple. Oopsie. This purple right here. And then the one in box 14 will be paired with the one in box 15. All right, and those are all the terms that you need to have. Now, let's try to get the function. The function f in standard sums of products form is going to be the blue group, this one and this one, will be what? The intersection of this strip and the 2 side strips. So this strip is A bar, B bar, A naught, B naught, in other words. And then the side strips will be just D naught. Okay? So A naught, B naught, and D naught. Plus, then you have the red group, these 2. Okay? This is the intersection of the column C naught, D naught, and A naught. Okay, this whole strip is A naught. Okay, so this one becomes now A naught and C naught, D naught. D naught. There you go. And we have that, and then we need the purple term, which is going to be these 2, intersection of these 2 strips, which is the strips C, okay, the strip C, and this row, which is AB. So you have ABC, ABC. Well, didn't work quite as I expected. So there you go, plus ABC. So this is the sums of products form for my function. And if I want to implement this function with NAND only terms, then all I have to do is take this SOP type expression and invert it twice. So I have to invert once, okay, and then invert, okay, where's my cursor? Um, and then invert again, different color, please. So this one should be a different color, like that. All right, so now I have for my expression um, that it is the following. These, with the first complement, will the ors will turn into ends. Okay, the ors will turn into ends, and then I'm going to have the complements, so the red complement broke up into pieces to go on individual terms, and also turned the ors into ends. And then this one remains intact like this. So now what do I have? I have NAND gates. Okay, this is NANDs. And then all of these three terms, the outputs of the first level NANDs, they all combine together into a final NAND. And that's it. Now regarding the complement function, for the complement function we're going to take the zeros. And the zeros here can be grouped as follows. I need a different kind of line. So this group here is the obvious one. Okay? And I have to take this group because of this zero right here in box number 5. This zero in box number 5 does not combine with any other term, any other bigger term. So this one here is an implicant. It is an essential, it's a prime implicant because, so it is an implicant. It is a prime implicant because it is maximal, so no other contains it. And it is an essential prime implicant because it contains this zero, which is not covered by anything else. All right, so that would be one of the groups. Then on to the rest. I need a different line. There you go. So there are a whole group of zeros down here that I can take all at once. As a matter of fact, this is an implicant. It is a prime implicant because it's maximal. No other contains it. And it is an essential prime implicant because of this zero over here in spot number 10. So I'm going to have to take all of this term right here. All right? All of this term. Now this leaves out this zero and this one that they have not been covered. So this zero, obviously, can only be paired with the one next to it. So let's find another color for that. So you can have this pairing. Well, it's not really that big of a difference in color, but it will have to do. And then I have this zero, which can only be paired with this zero over here. So I'm going to take I don't know, maybe a blue, and then I'm gonna take this. All right, so that's all. Those are all the terms. So the expression that I get now is going to be the following. The complement function is going to be this is the intersection of these two strips, vertical strips, and the first two rows. So A naught and D, okay? A naught D. Or the green term down here is simply this strip, okay, the horizontal strip like this, which is obviously A, B naught. A, B naught. Okay, so those are the maximal terms. Then I need this one, 7 and 6, which is the intersection of this horizontal strip, A naught B, and these two vertical strips, which are basically C. Okay, so A naught BC. So I have A naught BC. And then I have this term right here, the boxes 8 and 12, which is the intersection of these two strips, which are A, and this vertical column, which is C naught D naught. Okay, so this is or A C naught D naught, like that. Okay, so that is the complement function in SOP form. So now I can take my original function by taking all of this and inverting it. Okay, so if I invert all of that, if I invert all of this, all right, then I have inverted the complement function. Okay, I have now, with this inversion, I have inverted the complement function, so that is my original function. Okay, and then what I do is I apply the Morgan's rule. Okay, so of this becomes as follows. So the Morgan's rule will allow me to have, it's going to change the logical ors into logical ends. Okay, so like this. And like this. Okay, now, of course, I still need my complement. So let me put it back. I get my drawing and I draw my complement. All right. I'm sorry. I can't see. I drew such a nice complement all of a sudden, and it's just not right. So I'll have to. Let me see. I'm gonna have to slice that, but it doesn't want to work. So I'm just gonna have to redo it again. So the original complement breaks down into complements for the individual terms, which are these, and it has turned the ors into ends. Okay. By the way, we'll get to that later. But for now, I have to continue with applying the Morgan's rule inside these terms. So I have to copy that. Let's see. I have to copy this and use it over here. And now what happens is that these complements are going to be altering the terms that they apply to. So this is going to invert the variables and turn the ends into ors. So this is going to be inverted like that. So inverted or, this one is to go away, and then this one needs to be like this, then this and this, and then complement this, and then C, invert the complement like that. Okay, so this now is the um, product of sums form for my original function. Okay, now what happens if I want NOR gate implementation? I'm going to take the product of sums form. All right, I'm going to invert twice. The first inversion is going to take the it's going to change the ends into ors, and it's going to invert the individual terms that are in here. So it's going to turn all of these into nors, okay, and the ends into ors. Then I'm going to have a second inversion, and that is going to take care of it. So, for example, this is what I was going to have. I was going to have a line like this to indicate an inversion, all right, and then another one, a second inversion. However, the second inversion is going to turn all of this into ors. Okay, so let me redo this. Um, so this one here is the product of sums form, and then these inversions go here. Now, the first inversion, applying De Morgan's rule, what it will do is it will go away, and it will turn the ends into ors, so or and or, and then I'm going to have this one inverted, and then this one inverted, and this one inverted, and this one inverted. And as you see, now the whole result consists of only NOR gates. Okay, so this one is NAND gates starting from the SOP form. This one is NOR gates starting from the POS form. Okay, so these two examples are actually very similar to the homework that you will have to do on Kmaps, and I hope that it helps you understand how the homework needs to be done. At the same time, if you have any questions, you just need to email me and let me know. All right, that's it for today.